Hi, everyone. Thank you for coming. So my name is Omri. I've been in the security industry for about 15 years now, in all sorts of roles. And I also presented in past conferences such as DEF CON and AVAR. Today, we're going to talk about how adversaries are beating user protection engines. I'm going to give you some introduction, some technical details to get you aligned on the topic, and then we're going to cover the 3 major tactics and all of the methods inside of them, and wrap up with some conclusions. So what is a user mode protection engine? Basically, it's this kind of DLL inside of a process that siphons data, gathers telemetry, or manipulates some functions in all sorts of libraries to be able to control what the process is doing and monitor it. It can be done via instrumentation, like AMSI, or hooking. The reason to do that is basically because user mode code is usually more easy to develop. It's more stable. It won't cause blue screens. And you can do more things in user space than you can in kernel, because at least in Windows, there is patch protection, so you can't really do whatever you like. And also in the user space, you have the full context. For example, if you have an SSL application that sends encrypted traffic, it will only be visible in the user space itself. The major, most common technique to hook a function is using inline hooks. Basically, you modify the instructions in memory of the target function to divert it to your code and do whatever you like in it. And then you return it to the original function, or you can just return it to the caller itself. This is the most common technique that endpoint security-oriented tools are using, both commercial products and also other products and tooling that analysts are using, or other tools that analysts or researchers are using. Bypasses exist for a very long time, for more over a decade. But in the last 5 years or so, the usage of them is increasing quite heavily. If you refer to MITRE attack framework, you won't find a lot of details about it. It's only mentioned in like 1 paragraph in a specific MITRE technique. Okay, so let's start with the major tactic, which is hook evasion. Basically, how can you evade the hook? To do that, you have to find some way to execute the original instructions that are gone because they were overwritten by the hook, and then continue to the rest of the original function. So there's about 20 different techniques here that I grouped in 4 different classes, and we're going to go through them. The first one is called secondary DLL mapping. In this class, it's quite self-explanatory. The attacker will spin up in some way a different instance of the library he wants to use in a way that it won't be hooked. So he somehow creates in memory a second instance. You can see that there are the differences between the hooked and unhooked function. And then we'll just start calling that instead. There are 3 techniques to achieve that. Won't go into much details here. Basically, you can use reflective loading, or you can copy clone the DLL on disk and reload it again, or you can remap the DLL itself using the native NT functions. If you want to detect those kind of techniques, it's kind of easy if you look in the right place. In runtime, if you examine the call stacks, which not a lot of people are doing that, you can see that there are quite a lot of irregularities, DLLs that you'll expect to see in the call chain will be missing, or for instance, you'll see weird named DLLs. or you see the same DLLs but located at a different place. And for forensics, let's say if you got a memory dump or a clone of a machine, you can also find that in that way as well. Basically, reflective loading is quite easy to find, but you'll see that it's not for just any DLL. You see that it's a copy of a system DLL at the end of the day. And it goes this way for all of the other methods here as well. The next class is called binary restoration, or simply, in other words, unhooking. Just remove the hook, and you'll be good to go. But we have to find a way to do that. Once the DLL is loaded, because the code is overwritten with the hooks, we need to find some way to restore the original code. So that's how these techniques work. So the first class the first technique here has 3 variants. We just covered that. It's basically the same concept as secondary mapping. Just instead of leaving that code in memory and using it, just overwriting the original system DLL back and remove the hooks. If we don't want to go through the disk to get the code, we can also use other processes to get the code, either processes that will create, and they will load the code for us, and then we'll siphon it from them. For example, if we create a suspended child, we can rip out empty DLL from it, which won't have the hooks on it yet. Or we can debug it, and later the DLLs will load, and because we control the process, because we are debugging it, we can stop it before the hooks are installed and take the code out of it. Or we can just search an existing process that hopefully won't be hooked. The reason that is possible is because not all processes are monitored by security products or tools. It does have some other issues though. The next method is called section refresh, in which basically we're going to capture the state of the executable, and then we're going to refresh the code. First, we're going to obtain a section handle for the same module, and then we're going to remove it from memory and bring it back once. And in that stage, the code won't be hooked because the protection engine couldn't monitor it necessarily. And then we restore the data sections, and the code and the module will work once again. The next technique is called short circuiting. Basically, because the hook have to copy the original instruction somewhere else in memory in order for the function to actually work and the functionality to be kept intact, we can just try and find it in memory where the hook engine placed it, and then we can redirect the hook directly to that region, to that stub, instead of trying to copy the entire code entirely. Or we can override the trampoline itself, which will be a bit harder to detect. And then the hook engine, the protection engine won't be called, and effectively we kept the original functionality intact. There are, as we can see, there are runtime indicators here as well that we can pick up on, though significantly much less. And also in forensic stage, we can detect all those methods. Basically, since hooks are removed, it's quite easy to pick up on. There is a relatively new volatility plugin that tries to do exactly that. I can include a reference to it at the end of the slides. And also for short circuiting, well, the hooks will be changed, so it's kind of easy to pick up on when you analyze the code in memory. Now, the issue with all of these techniques so far is that they rely on system calls. So the system calls can be monitored as well. So we have to figure out how to evade that as well. So the way a system service works is, in Windows at least, that you have to place the index of the system service you want from the kernel on the EAX register, and then use instruction to transition from the user space into kernel, which is either the syscall instruction or the int2e. Quick word about it. The int2e instruction was the legacy method that that Microsoft chose to work with, but they brought it back with the introduction of VBS, virtualization-based security, on Windows 10 due to performance considerations. So there are two methods in user space to do that. So we'll be aware for that on that for later. All right. The first technique here is basically, since the index is in a specific instruction, we can just parse those instructions. We get them from the disk, okay? Get the clean code from disk, parse it, and then extract the index, and then it will just work quite easily. And there are also other methods to do that. For example, if we don't want to access the disk, we can see a side-by-side comparison of a clean NTDLL and a hooked one. And you can see that the instructions that the system services are placed in an ascending order in memory, okay? So you can basically just count to the function you want and get the index of it without parsing the instructions themselves. You just have to walk across all the exports, create a sorted list, and then you just look for the system service you want, and you have the index itself without parsing instructions. Or if you're lazier than that, you can just skip right ahead to the function that you want, and if it's hooked, just check one of its neighbors and extract the index from it. The next method is called Evans Gate. It's a very specific case for a 32-bit process on a 64-bit machine. The reason for that is in order for 32-bit to run on a 64-bit machine, there is some compatibility layer, some translation layer that is called the WoW64, Windows on Windows 64. And it creates us some opportunities because NTDLL, for instance, will be mapped twice, one with the 32-bit instance version of it and the native 64-bit instance as well. The first variant here we can do is to skip the 32-bit hook eventually and directly go to the native NTDLL if we implement the transition to 64-bit ourselves. And the second variant is called completely native. Again, you can use all of the previous parsing methods and just directly go to the system calls in our code. The next technique is called end-to-OS kernel parsing. If you think about it, NTDLL is the interface to the kernel, so it means the kernel need to have the same translation table for the system services. So basically, we can find the same index at the kernel binary. All in user space, by the way, no need to touch the kernel itself. We start with the ZW exported functions. They have, at least in the kernel binary, those are the functions that have the index itself. So basically, you can parse it for the same instruction and for the same instruction pattern of the MoveEX. And the functions are exported, so you can just call get proc address to find it. For functions that don't have the functions that don't have the ZW version exported, but have their NT version exported, we can do another trick, which is locate the same translation table, basically the SSDT table, even though it's not exported. What we can do is find a couple of pairs of ZW and NT functions that are exported, get the index and get the offsets from the base, and then try to look for this array that will match the index and the offset value to find the base of the SSDT. Once we do that, we can go to the function that is exported but don't have the ZW function variant, and then calculate its offset and just traverse the table and get the index. The limitation with this technique is that, well, it doesn't have all of the functions in NTDLL available in the same way, but it's still quite good enough if you're a malware developer. You can get all the functionality you need. Next up, the next technique, if we don't want to do all of this complex parsing and everything, we can just bring the index ourselves, hard-coded ahead of time. It does have some issues because the service index is not guaranteed to be the same between each OS build. So you have to take account for it, and for each version of Windows you want to support, or the attacker wants to support its target, as its target, he has to prepare in advance. All right. And so far, most of the techniques required quite a lot of hassle. So there is some more clever and easy way to do that. Instead of doing static parsing or work ahead of time, you can just use dynamic resolution. And basically, because the EAX register will hold the value, we can stop at the point of the syscall. Okay, we'll use an exception handler. We'll place a breakpoint, a hardware breakpoint on the syscall instruction, and then run the function. And once the breakpoint will hit, in the exception handler, we'll get the context, the thread context, and we can extract the EX value from it, and then we can just go ahead and use it. Regarding detection, so as you can see, for forensics, there's not a lot of much to go on, but for on runtime inspection, well, the call stacks will still be different, so there's a lot of opportunity there. And also, as I mentioned, specifically for Windows with VBS enabled, if you check the actual instruction that made the transition, well, in the call stack, it can reveal this kind of those methods because most of the implementations are quite sloppy and they don't really take into account of that new change. So for the last class under this tactic, which is called code splicing, basically the point here is the idea here is to rebuild the function in a different, the function stub in a different place. So even if the function is hooked, nothing will go through the hook itself because we'll never will call it directly. So we use reflective learning for that. We get the clean code, we copy out the stubs, and from there on now, we're going to use them instead. So even if there is a hook, nothing will happen. We can use other variants that I mentioned before, like section remapping or clone DLL, but those will just create detection opportunities. The last technique in this section is called stub reuse. Instead of accessing the disk, which there's no really point, again, because we discussed it, the stubs are already in memory in case the function is hooked. So you can just find it and then just use it directly. There's no really need to do a lot of heavy lifting. Detection-wise, well, if you inspect the call stacks, you won't see any differences. And also, you don't really have forensics artifacts to go on here because it uses the same code that is already there in memory. So we are done with this tactic. Now we'll go into argument forgery. If so far we try to evade the hook, now we're gonna let it be, basically, and we'll try to outsmart the protection engine. The way to do that is that you can still call the protection engine, still go through the hook and go through the monitoring, but provide it with fake arguments. And then once the protection engine itself calls onto the original function, swap them to your malicious arguments, to the ones that you actually want the function to use. And the way to do that as well, as we discussed before, you can use hardware breakpoints, just like previous techniques, or you can provide an argument that will cause the protection engine to trigger an exception, but that's a less likely option because it's quite highly dependent on the product's code. So if we look on how it works, we set up the exception handler, we place a breakpoint. I put the two variations of the function with and without the hook, so we can see it clearly, on the place that the protection engine will return to. Okay, it's at the 7+7 offset. Place the breakpoint and call the function with the fake parameters. Okay. Yeah, if we look, for example, for the Internet Open URL example, the second parameter is the URL. So we pass through the protection engine, and we see that the argument didn't change yet. Once it calls back to the original function, the breakpoint will hit, and we'll edit the arguments, change them in the context structure, or edit the stack. And we can see that we swapped out the URL, and remove the breakpoint if you want, and just continue execution. Well, if we look at detection here as well, it's kind of easy to pick up on. If hardware breakpoints are used when no debugger is attached, it's quite unordinary. And also, we have the specific address of the breakpoint, so we can figure out if it's on a hooked function or not. So it's quite easy to figure out. And the major shortcoming of this method is that because it has a clear indication in runtime, and the protection is still invoked, it has a pretty good chance of not only detect it, but also prevent it. Okay, so we're getting close to the end of our of the content. We have one more tactic to cover. This one is called engine disarming. If so far we discussed on how to remove the hooks or how to trick the protection engine and the monitoring logic, now we're going to try to look how we can basically dismantle the engine itself, the same DLL that is loaded for monitoring. There are variety of methods here. Well, the first one, since we loaded DLL, can just try to unload it, either with free library, which doesn't really work anymore, because at least you hope that the vendors that provided the engine accounted for it, because you can provide a flag in the loading phase that will prevent unloading it. Or you can just look, but that's a vendor-specific functionality, just look for the unload function inside of the engine. The second method is to unmap all of the DLLs in the process. Kind of like section refresh, just not with returning the code into memory. But that's not really feasible long-term, because you remain with a process that doesn't have any libraries loaded into it. Not a lot of functionality that you can perform. The third method is using, at least on Windows, the mitigation policies to allow only Microsoft signed DLLs to be loaded. And the fourth one is basically doing the same thing, but not with OS functionality, but by preloading in a new process. You run your own process and you run the payload in it, which is very common for many malware to actually perform. But you control it, again, as we mentioned, either with a debug process, and then you can just break once a library is loaded, see if it's a library that either you don't expect or you know it's in a certain blacklist. And then you can just overwrite its entry point, return it to do nothing, and the product will kind of be disabled. Or you can inject into the process instead of debugging it. You can use certain callbacks that are internal in NTDLL and will probably run before the protection engine, and then hook functions like the LDR load DLL or the APC dispatcher, which a lot of products use to inject themselves into user space, and apply the same logic to see what runs, either a blacklist or something similar. There are other methods that can be used that are, though they are vendor specific because they depend on the implementation. Let's say if the hook engine has some flag in it, that internal flag that says if it's enabled or not, and you can just flip it, and all sorts of this kind of methods, but it's not generic. And luckily, all of the generic methods can be quite easily detected in runtime. If you know from the defense perspective, if you know you loaded up or intended to load up the protection engine inside the process, and for some reason you don't see it loading, or after it was loaded, it's now disappeared, it's quite easy to figure it out. So that's all of the content here, all of the methods that attackers use. And let's cover up some conclusions that we have so far. In addition to the fact that it's quite easy to bypass all the hooks and the security products, using user mode code has its own limitations, or only user mode components has its own limitations. You can't provide protection or monitoring at boot time, or if somebody started before you, you have an issue. You can't really protect yourself. You can't really protect your product or your solution in a strong enough manner. You can't really build hardening without running with higher privileges. You don't have access to other OS processes or critical processes, so the options you have to monitor or the data points you have to monitor are becoming more restricted. You can't really monitor for RPC, privilege escalations, and stuff like that. And also, if you go with monitoring that is built on components like ETW, so you have a problem to react fast enough. ETW, for instance, is deferred, so you get the telemetry only after the operation has happened. And also, it doesn't really protect you against blue screens. If you crash a critical process, then you still have stability issues, so you have to know about this. The last slide for today. As we can see, the techniques that we covered are very easy to implement. If you go online, it's likely most of them have open source available for you. A lot of them share the same concepts and constructs. I believe I repeated myself quite a lot during this session. We can see that this kind of post-exploitation technique, it's likely the most prolific one till date. For my count, I think there are more of these evasion techniques than of code injection techniques. If you are having the attacker try to evade like the runtime inspection, for instance, and try to evade your detection of the indicators that we mentioned, because most of them are relying on the call stack. There are methods to address that as well. If you use the shadow stack, for instance, or if you implement your own sandbox or emulator, so you can implement a transition-based code tracing and build the call stack yourself. And the final message for today is what I believe should be clear enough after this, is that user mode hooks are just not enough for security. They have a really, really big design flaw that they rely on the same environment that they are designed to protect. I have the reference slide. This is the one slide. If you want to take a picture, the slides I think will be available online later. And the second one. And thank you.
Is there any question from the audience? Please raise your hand or approach the microphone. Going once, going twice. Okay, then thank you, Omri, for your great talk. And now we have a 10-minute break before the next session starts. Thank you very much.
Thank you.